Okay, let's prove triangles are congruent by side, 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 side angle, side, and hypotenuse leg. These examples are answering the question, how are triangles proven congruent? And we'll have a variety of examples including two-column proof. So let's look at some multiple choice. Name the angle included by the sides MT and TR. So here's the angle that's included. How do we name that? T has to be in the center of the angle name. So B is out and C are out. B and C are out. MTR or RTM are our two choices. So it looks like choice A. All right, given the diagram and the notation, are these congruent triangles, and if so, why are they congruent? We can see the markings showing the two sides and the two angles are congruent. Well, also, the two triangles share this side here. So that side is shared by both triangles. That's a congruent side as well. So now we just have to look at the order of the sides and the angles. And this is actually an example of the infamous side-side angle. Right? So we have, if we go sort of in order, if this is triangle 1 and this is triangle 2, let's follow the order of the congruence in triangle 1. So first we have a side and then a side and then an angle. So that's side-side angle. If we look at triangle 2, we've got the same thing. We've got this side followed by this side followed by the angle. So the infamous side-side angle approach, which we know all too well, does not prove congruence. Okay, what additional part would make the following two triangles congruent? Again, like the previous example, we have this shared side DB in both triangles. So you can see, again, if we're looking at, let me make my colors the same. So here's triangle 2. I'll go back to red, triangle 1. So if we look at the sides, we've got side, side in a row. If we could do side AB there and make that congruent so that we have side, side, and then a third side. If we could make AB, 3, congruent to DC, or to CD rather, that's going to show congruence, and that's going to be by side, side, side. So that's looking like a good option. But now also, if we don't take that approach, what else will get us the congruence? Because it doesn't have to be three sides congruent. Well, another option is to do something like side angle side. What would be required there is we would need in triangle 2, we'd need this shared side, this angle here, and we already know that side BC is congruent to AD. So what we really need is this angle congruent to this angle, and that looks like B as well, and that's going to be by side angle side. So B and C both look good, which means ultimately, if we read through our list of choices, it's going to be E that shows up as the final answer. Okay, is this enough information in the diagram to prove the triangles are congruent? Well, just by the orientation of these two triangles, you'll see in situations like this we've got vertical angles, so those are always going to be congruent, so that's a good place to start. Now E is the midpoint of AC and BD. Midpoint tells us that AE is congruent to EC, and that DE is congruent to EB. Is that enough information? Look at the orientation of our congruence. We've got a side, an angle, and then a side, congruent to a side, an angle on the side. So yes, by side, angle, side. All right. Can we draw that up as a complete proof? 2 columns, statements, and reasons. This is going to follow the exact same order that we just discussed, but now with an official 2 columns. So E is the midpoint of AC and BD. That's given. That creates these segment congruences, and that's by the definition of the midpoint as we saw. We know these angles are congruent, again by the vertical angles theorem, and now we can conclude the 2 triangles in the specific order AED and CEB, and that's by SAS. All right. Given MT is congruent to RQ, and that RM is congruent to QT, prove the 2 triangles are congruent. Well, we've got 2 congruent sides, and we haven't even mentioned the shared side, which we know has to be congruent. So it looks like we've got our proof informally. Let's see what it looks like written up as 2-column proof. Always start with the given statements. RT is congruent to RT. Why is that? That's the reflexive property, and that's all we need by side, side, side to prove the 2 triangles congruent. Okay, here goes where we got 2 triangles sharing a vertex and vertical angles. Let's see if that comes into play if we have parallel lines AB and DE, and we know that those segments are also congruent. C is the midpoint. Okay, so this example is going to include some of the arguments we've already seen in previous examples. Let's see what we have. First, always start with the given. Now AC is equal to CE. We're going to use the definition of the midpoint there to prove those side congruences. Now angle A and angle E are congruent. Now why is A here congruent to angle E here? Well, given our parallel lines being cut by a transversal here, angle A and angle E are in a very specific position there on either side of the transversal, and that's the alternate interior angles are congruent with parallel lines. Okay, so we've got some side congruences, we've got an angle congruence. That's enough for our triangles to be congruent by side, angle, side. We didn't use the vertical angle, and the reason why we didn't use the vertical angle is if we talk about side AB being congruent to side DE, that's given. If we talk about AC being congruent to CE, definition of the midpoint, and then we talk about these angles being congruent, that's again our infamous side-side angle. Don't want to use that. That does not prove congruence. Okay, now we've got an example involving perpendicular lines. So AB perpendicular to AP. We've got AB and BP being congruent segments. Let's see if we can't establish congruent triangles with that information, starting with what's given. Now, angle MBA and MBP are right angles. That's the definition of perpendicular lines. Okay, if they're right angles, that means they must be congruent. The right angles congruence theorem. Both angles are 90 degrees, their measurements are the same, they're congruent. So we've got angle congruence to go along with our segment congruence that was given. A third segment is shared by both triangles, MB, so that's the reflexive property, and that's enough for side, angle, side. Okay, we've got two overlapping triangles, two overlapping right triangles, and let's build our two-column proof. WY is congruent to XZ, so these are the diagonal segments are congruent. WZ is perpendicular to ZY, XY is perpendicular to ZY, so that's indicated in the diagram, excuse me, the right angles. Okay, so that's given. Now, angle Z and angle Y are right angles. Definition of perpendicular lines, that means they're congruent, and the base ZY is shared by both triangles, and given the right angle there, we've got the two triangles being right triangles by the definition of right triangles. Here's your ZY and YZ. That's the reflexive property. That's the base. That's enough information to prove the triangles are congruent. We've got the hypotenuse is given to be congruent. We got the leg, and we've established a right triangle. We've got the proof by the HL congruence theorem.